Um, so, welcome for the second talk of this morning. It is by Justin David from IISc, and he'll be telling us about unitarity and bounds in conformal field theories.
I thank the organizers for this opportunity to give a talk, and I think we are the closest to ICTS, and perhaps it's only now I could come, so apologize for that. But so I'll be talking about this topic, and this is work done with Shubham Datta Chaudhary, who's a student, and Sri Roman, he's here, and also I'll be talking about another work with Surbi and Prem, who's at Swansea. And some people might have heard this, but maybe towards the end I'll talk about some current work. So let me start with some motivations and something just to get our bearings. So if you recall, most of us are familiar with D equals 2 or conformal field theory, and using the Virasoro algebra and just the positivity of norm. These are some things you learned very in the initial, just when you study Virasoro algebra, you can show that using positivity of norm, that the conformal dimension of any primary is greater than or equal to 0. And also using, again, the Virasoro algebra, you can show the central charge is also greater than or equal to 0. Now, if people are familiar with N equals 2 superconformal algebra, which admits a U1 current, and there are similar algebraic methods show that the dimension of primary is greater than the charge. So, so the constraints, if you just see, though it comes from this unitarity constraint, it is of two types. One is constraining the theory itself, like the central charge of the theory is greater than or equal to 0, and another one is constraining the states within the theory. Okay. So these are two kinds, just to bear in mind. Okay. And what we will discuss in this talk is basically constraints of this nature, and one such constraint is a constraint in the space of all D equals 3 conformal field theories. Another one, this is of the nature of the first constraint, where we are like central charge is greater than or equal to 0. And the second constraint is that of the states carrying spin 3 charge in a large CCFT with this particular symmetry, W3 symmetry. So these constraints, though the way we arrive at it are quite different from the naive way you saw how these constraints were derived, just the Virasoro algebra constraints, for instance, where we impose positivity of norm. The way we arrive at it is seemingly different, physically different, but they are related. In some cases, we'll be seeing more hint about the relation, but in some, we haven't proceeded that far. And the chaos bound is also an example of such constraint, and we will discuss its violation actually when states do not satisfy such constraint. So let's start with the 3 dimensions first. So in 3 dimensions, so just to set our thing, so the 3-point functions of any stress tensor in a conformal field theory, people might be familiar here, lots of conformal field theory was discussed. So are constrained in this manner, just by conformal invariance, that you can break up the 3-point function as in terms of 3 terms. And the tensor structure is such that one tensor structure is the tensor structure you obtain while Wick contracting free boson theories. Okay? And there's a coefficient in front of it. And another tensor structure is that when you do Wick contractions of free fermion theory, there's a coefficient, and similarly a free vector theory. This is in 4 dimensions. So this breakup was found by Osborne and Petku long before ADS CFT. And it's sort of, it's very, I mean, the theory is completely specified, at least for this 3-point function, by these numbers. And these numbers need not be integers. For free theories, they are integers, but they need not be integers, and they can depend on the theory. Okay. And Hoffman and Maldacena in 2008, they devised a thought experiment to actually obtain constraints for these parameters. And these constraints allow one to find the space of allowed conformal field theory. Now, similar constraints can be placed for such correlators. Okay, here there's 2 currents with the stress tensor in between, and they do. I mean, Maldacena and Hoffman also find constraints for this in D equals 4. Now, such constraints, of course, has been explored, heavily, both in holography as well as in CFT. And what we will do is explore this constraint in D equals 3. And what's so special about D equals 3 D equals 3, what happens is that this breakup, which I mentioned, that it breaks up into free bosons, free fermions, there's a parity odd structure here. Okay. Similarly, for this, there's a parity odd structure here. It was found by these authors. And so therefore, I mean, if you think about it, if you take into account the normalization, this conformal collider, there are 3 parameters here. And if you take into account of the normalization, that these collider constraints will restrict the theories in this 2 parameter space. Okay, if you remove the normalization. Okay. So this structure, this fact that there was a parity odd thing was ignored. And so what we will do is basically initially look at this and find what the constraints are. Okay. So let me just recall the conformal collider experiment. Maybe many, yes, yes, yeah. JTJ. JTJ, the right hand side, these are T. Oh, sorry, I cut and pasted this. Sorry. Yeah, so no, this should be JTJ. And these NAs are different. Okay. These are J's actually. Yeah, this should be, yeah, sorry. This is JTJ free boson, JTJ free fermion, and so on. I mean, I just cut and pasted this. So, yeah, sorry. Yeah.
There is only one parameter.
There's only one parameter.
So that's not normalization though.
Which for this case, JTT, yeah, there's only C, central charge.
Yeah, but you cannot get rid of it just by normalization. So
that you cannot get, yeah.
So how is one get rid of one of them?
Yeah, well here, yeah, I don't know in 2 dimensions how it works actually in this case. Here, okay, I'll show you. I'll show you how it works actually. Yeah. So the conformal collider actually, so let me repeat the experiment again. Many people might be familiar actually. It's good to see in a picture actually. So the experiment is roughly speaking. So you take an excitation in the middle, in the origin. Say we are in a 2+1 dimensional theory. So time is forgotten and this is the 2 real space. So you take an excitation and you keep a detector in a specific direction, n hat. A specific direction, and you measure the energy here, and you integrate it over time. Roughly speaking, that you measure the energy of this. So this pulse expands. You measure the energy coming out, and you integrate that energy over time, and you demand it is positive. That's roughly the experiment. So let me just explain it. This is just a picture to keep in mind. So here, so one considers a localized excitation. Say the origin, okay, and the excitation propagates outside, and you keep one detector at some particular direction, okay, and measure this integrated energy. So this is what you measure. So this is the the state which you're making the excitation, and you measure this particular object. What happens is that we take this O to be created by the stress tensor or the current, okay. And the requirement that the energy measured is positive is the conformal collider bound. So of course, taking this O operated to be stress tensor or the current, it goes to the 3-point functions, TTT, and that's how the constraints will come in. Now, so it can be shown, though I can't go through it now, but it can be shown that the fact that you're keeping this at infinity, far away, it actually, this detector hugs the scribe plus and the scribe minus actually. This whole process of integrating over time, when R is pushed to infinity, okay, can be transferred. You can show that it's actually an integral over the scribe plus or the scribe minus, yeah, here, okay, at asymptotically infinity. So you can show that it actually reduces to this integral, okay, instead of just on the sphere. Okay, so this is a non-trivial fact. I think Hoffman and Maldacena show this. Okay, yes. In the CFT itself, yeah. There's nothing. Everything is CFT. Okay. So this integral is, and the condition on positivity of this integrated energy flux is called the average null energy condition. So let me say what are the excited states. So this is the thing you are measuring, and what is the excited state? So the excited states are basically defined by inserting an operator with a particular energy. Okay, so you take the Fourier transform, This I'm doing it in 3 dimensions, dx, dy, dt. This is the way the excitations are defined. And we choose the excitation to be the stress tensor or the current. Okay. And by the conservation law, okay, of the operator you're inserting in, there is actually like 3 independent polarizations for the stress tensor. In fact, they should be spatial, and the fact that they are traceless, you can use that to show that there is 3 independent polarizations. And remember, there is one specific direction already chosen, and everything is measured from there. And in d equals 3, there are 2 independent polarizations, okay, and 2 for the current. So suppose the independent polarizations are some epsilon alpha, okay, some linear combinations of the polarization, and then you construct this particular matrix, okay, of various polarizations of this operator and various polarization, and you measure this energy flux. And so you get this matrix, and the requirement that the average null energy condition is positive turns into a condition on eigenvalues of this matrix. So let's recall, okay, the conditions. Okay, so this is what. So let's just keep this in mind. So our operators are basically stress tensors or the currents with definite polarization, and we are inserting them and measuring this energy. And let me proceed. Okay. So let's recall what Maldacena and Hoffman found for d equals 4, and this pattern is sort of same in higher dimensions also. Okay, and here is where the normalization comes in. So let's recall this condition what they found. There are 3 independent polarizations for this matrix, okay, in d equals 4, and it's true even in higher dimensions. And then you remember there was this NV, NF, and NS, and you define this particular combination, okay, T2 and T4. I think they only found this particular combination, T2 and T4. And here this is the normalization. This actually comes from the 2-point function. Okay, you define this, and then the constraints can be written in this manner. They are linear equations. There are 3 linear equations, and this is the constraint. So let me just plot this just to see the constraint. So it's a triangle. People might be familiar already with this. Oh, this is green. So it's a triangle of this kind. Okay, this is line 1, line 2, and line 3. And this line is where the theories for vectors is equal to 0. And this vertex is interesting. This is a theory with for instance, vectors is equal to 0, fermions is equal to 0, and scalars is a free theory, and scalars not equal to 0. And similarly, other vertices are there. Right? And Einstein gravity is actually at the center. Or any theory which is dual to Einstein gravity is at the center, and these are free theories. Okay, so I think here this NV is not equal to 0 and the rest are 0, and NF is not equal to 0 and the rest are 0. Huh? Yeah. Oh yeah, that's what I'm taking it is free, because there's only scalars. The 3-point function just gives you just the free scalar Wick contraction answer. Does that mean that? Yeah, maybe at this level the 3-point function is same as the free theory. Yeah. Yeah. Yeah, no, gravity dual, 2-derivative gravity dual is here. Okay. Yeah, that's another reason they chose this T4, T2 parameter. It's a nice parameterization with just the origin is gravity and everything else deviates from it. Actually, it's a good parameterization. Yeah.
Not constrained.
It's not constrained.
Physical thing.
Yeah.
But
it's not constrained. It's not constrained. Yeah. But the ratio comes in such a way that there are 2 parameters.
Yeah, he's not saying that. Yeah. I mean, he's not saying that NS and so on are only defined up to a normalization.
Yeah, no.
They're well defined, but it's only the ratios that are constrained.
Yeah, that's true. Yeah. In D equals 3, we have, as I said, 2 independent polarizations for both charge and the stress tensor excitation. And we have therefore a 2 cross 2 matrix we have to look. So I said we take all the polarization matrix, all the independent polarization and construct this matrix. And so we have a 2 cross 2 matrix. And so here's the structure as I wrote. So we have chosen this direction to be y, say, the direction you're sitting the observer is y, and here is the, for stress tensor, sort of the polarization. You can choose x, y is 1, and here is the, like a tracelessness, x, x is 1, y is -1. And you construct this polarization matrix, okay? And of course, this epsilon is this operator where you integrate it, okay, as chi minus, x minus, and you push it to infinity, at infinity, and you'll have to do this integral. And this is the 3-point function. And here's the, you have to norm the states, so this is the norm. And of course, all this requires regularization, and they, Maldacena and Hoffman, provide the regularization, the I epsilon regularization for doing this. And similarly for the charge, there is some matrix. And just to see, just to show you the difficulty in evolving it, or the amount of work one has to look at, is that these correlators are large. There are various tensor structures. Okay, and where is the parity odd? This is the parity odd here, for instance, and the epsilons are hidden in the S's. And there's a lot of parity structures there. This is the all the tensor structure. And everything, of course, all the coefficients in the tensor structures are given by NF, NS, and so on. And here is the matrix finally. Okay? After you evaluate it and carry out all the steps for evaluating, this is the matrix. Okay? This is for the charge excitation. So here's the charge excitation, and we are evaluating the matrix. And this is it. The trace is positive, and these are the relations. So this coefficient is related to the fermion and the scalar. The coefficients in the 3-point function. This is the parity odd part. So you see, the parity odd part actually comes off diagonal. This is the first instance, where the thing comes off diagonally, the matrix comes off diagonally. And if you demand that the determinant or the eigenvalues are positive, which essentially translates to the determinant is positive, it turns out that these coefficients, A2 and AJ, has to lie on a circle inside a disk of radius 2. Okay, so unlike in 3 dimensions and higher, now we have a disk, okay, with 2 parameters. What do I call it? Alpha 2 and A2 and AJ. So it's a disk, and similarly, you can carry it out. So it's a disk with this radius, and all the theories are lying inside this. All the theories which satisfy average null energy condition. And similarly, if you do it for the stress tensor excitation, again you carry out the analysis. The analysis is a little bit more involved, but you carry out the analysis, you will get this matrix. Okay, and again the condition is that the eigenvalues of the matrix being positive is again a region which is a disk. Okay, so there is this 2-parameter space, and it has to lie in a disk. Now, of course, and one can show that this one is Einstein gravity here. This is Einstein 2-derivative gravity. So, but what is on the boundary? Okay, what is the one which saturates the bound? So where does this? So this is where the Large N Chem Simons come in, and the Large N Chem Simons, people have worked quite hard actually. They have evaluated these numbers in the Large N calculations, and exact Large N calculation. They have got these coefficients, okay, for these theories, and I'll tell you some history about them. But these coefficients are known, and here they are. These are the coefficients. There is some ambiguity. There was some ambiguity, but we had fixed it. But there was some ambiguity in the proportionality constant here. But overall, in the full Tooft coupling is completely determined. Actually, you can see that this is the Tooft coupling, and they are nice functions of this kind. Okay. And you can see that this parity odd is actually it's in fact one loop. Okay, that's another thing to note. One loop in the Tooft coupling. And let me tell you the history of this calculations, okay, which is quite amazing, because you have an exact answer to all orders in lambda Tooft coupling. So the existence of this parity odd term for this particular class of theories was initially confirmed by these authors. Okay. And the full 't Hooft coupling was determined by, by arguments by Maldacena and Trivedi, and they were perturbatively checked to all orders in the 't Hooft coupling by these authors. But these analyses can, in principle, fix the normalization. Actually, this Maldacena-Trivedi analysis, but there was some discrepancy in the literature in this normalization. But so we redo the analysis actually, and some factors of 3 and 2 were after solved. But we find these factors actually for this particular. After fixing the tensor structure, we find these factors. Okay. And then you plug in because you have now. Just it's very simple. You have now all these things for this particular theory. Okay, this NF, NS, all these numbers you have for this Large N Chem Simons, and you plug in, and where do they lie? They lie on the boundary of the circle. Okay. And the angle is actually the 't Hooft coupling. I mean, a particular theory lies on that particular point in the disk, a particular value of the 't Hooft coupling. So in fact, this is the picture. Okay. All theories in 2+1 dimension or of this kind, they have to lie in this parameter space. They have to lie in a disk, and the free fermion and free boson are here, and these are the interacting free fermion. This is the Chern-Simons basically bounding the whole disk. So this is the nature of this constraint. And of course, we don't have very much to say about the unitarity relation here, but we are working on it. And one more thing I have to add, that such conformal constraints, in fact, where there's a matrix involved, has been generalized after our work by these authors. And more importantly for us, actually, is that they confirm the saturation of the bounds. Because for us, it was, when we did it, it was really a factors of 2 and 3. And we were sort of, okay, we were a little confident, but we were not, there could be a possibility that they're not saturated, but they also confirmed that saturation of the bounds by the Large N Chem Simon. And the fact that the Large N Chem Simon saturate these bounds is also related, because you know that in these theories, the unitarity bound is saturated at the leading order in M. So there must be a connection between the fact that you got these bounds for these theories to unitarity, and this is one thing which we are exploring actually. Yes. Yeah.
Move inside.
It should, yeah, but we don't have a theory to check actually.
But the guess would be that the variation in 't Hooft coupling and N just fills out the whole thing.
Well, I don't know. There are all theories, all possible, like, Ising model and everything. Everything is lying inside.
Yeah, but in particular, this class of theory.
Yeah, I don't know whether it will cover it. Actually.
Okay.
Yeah, I'm not sure.
Okay.
Cover it. Yeah.
And do you roughly know where the Ising model is?
Yeah, I think in that Maldacena paper it's written. I haven't looked at it, but they have located the Ising model inside actually. Yeah.
Your disk.
In the disk. Yeah, in the disk. Yeah. Okay, so there is now I will go to 2 dimensions where there is a similar constraint. This is the nature. This is like the second kind of constraint. This first constraint is constraining, spaces of all theories, right? We are saying all the theories in 2+1 dimension lie here, but now we will go to the second nature of constraint where you're constraining states. So again, the setup is very similar to what Maldacena and Hoffman did. So here, what we do is we consider. So this picture is actually good. Yeah.
The origin is a special significance, right? Unlike in 4D case where it was a parameter specific thing.
Yeah, right.
But what is it? The
this
origin?
Is, gravity again. Gravity. AVJM model, for instance, lies here. Einstein gravity is here. Again, yeah. AVJM model is here, right?
Sorry, so you made constant on JJT. Is there any JJJ, any general like arbitrary spin?
Yeah, arbitrary spin also we believe it's constrained, but I don't think it has been explored. Yeah. In fact, it is good to do it because the normalizations are not fixed for that arbitrary spin, 3-point functions and so on. And it's good to do it because you can fix those normalizations. anyway, so I will, so now we will actually slightly look at a different constraint. Okay, I've got the spelling wrong, but slightly different constraint. But again, it's constraining states within this theory. And again, the way we arrive at these constraints is very similar to what Hoffman and Maldacena did, but again, not directly related to some unitarity matrix. So the setup is similar. So we consider localized excitation, okay, in the theory. So this is 1 plus 1 dimensional theory. So we have this localized excitation. It's a pulse which we create by inserting an operator O, primary operator of dimension delta. Okay. So it's created at x is equal to 0, at t is equal to 0, and then it evolves. So we evolve it in time. So it travels on the null cone. Okay. And then we observe the entanglement entropy between L1 and L2 after time t. So this pulse sort of spreads, and it in fact breaks into two immediately, and then it spreads on the light cone. And then we observe the change in entanglement entropy as it enters the interval. Now, just the details of it. So how to set up this excitation again, just like the way we set up here. So here it is. So we take the theory at finite temperature, actually. So there is the density matrix for the finite temperature. We insert the operator. Okay. We smear it, I mean, the fact that we have to give a finite width, we have to smear it a bit. Okay, so this is the smearing part, and then this is the evolution part. Okay. So this is quite easy to understand, at least this density matrix. And then one can verify by evaluating that, the trace of the stress tensor in this row, trace row, I mean, the expectation of stress tensor in this, it actually has this particular feature of a pulse moving in the light cone. And the jump in, and of course you would expect that once this guy enters this fellow, here, once this pulse crosses this, the entanglement entropy jumps. Okay. And in fact, the jump can be evaluated for large CCFT. In fact, for even finite CCFTs, if you know how to handle them for these correlators sufficiently, you can handle this. But for large CCFT is what we are interested in. And we can evaluate the jump because we can evaluate it using some heavy light correlators for this. Okay. And equivalently, it can be thought of as there is a holographic dual to this whole setup. And that's what is interesting. There's a holographic dual, but it's equivalent. It's really equivalent. And the holographic dual is quite interesting. It's essentially, so we have an entangling interval, and then there's a BTC black hole because the theory is at finite temperature, and you release a particle. So this is the excitation. Particle of mass m, which is proportional to the dimension, and you release this particle, and there's an entangling interval, and you can observe the change in entanglement entropy. And this can be done exactly even in the geometry, actually. This time-dependent back-reacted geometry was initially found by these authors. It has been refined by them. Okay, it's essentially you have to go into the geodesic of this infalling observer and write down a geometry. And you can evaluate the entanglement entropy, and this is the profile. It sort of jumps. Okay, you remove the finite temperature entanglement entropy of this interval, and you observe it in time, and it jumps in this particular manner. Okay, and this jump. This jump is here. So this is a jump, and to obtain a simple expression for this jump, I mean, of course, you can plot it and so on. But so suppose you want to like a nice compact formula for this jump, you can take this particular scaling limit. So you take this pulse, the width of the pulse to 0. Actually, sorry, this is what happened when I wrote it very quickly. So epsilon to 0. Okay, and the density is given by roughly this. The density in that particular state where you created the excitation is delta by epsilon squared. And therefore, if delta is scaled like epsilon e by pi, pi is just a normalization, then the total energy is fixed. So we keep the total energy of the pulse fixed and send in the pulse. And if you do that, we get a nice scaling limit for the jump. So this is the jump for large times. Okay. So there is this feature. Okay. Now, what if you do this? Yeah. Delta? Yeah, eventually it is scaled in this manner, epsilon e by pi.
But don't you, I thought you were taking delta to infinity.
Delta, yeah, so delta, sorry, yeah, so of course we use the heavy, that's what I understand you say. We use the heavy light correlator. The light correlators are basically the, the Wilson, the geodesic, okay. Basically, let me tell you. Okay, so let me tell you all the correlators involved. So this is the twist fields. And this is the delta. This is the delta.
Right.
So there, the delta is of course delta by c is of order 1. Delta by c is of order 1. So this is what we take. And here the twist is of something like n plus 1 by n, c by 24, or n minus. So this is going to small. Okay.
But
that's why we use the heavy light. Yeah.
So, but delta over c is like epsilon, so that's going to 0.
Yeah, eventually after, yeah, there is, so this is to take the back reaction into account. So we evaluate this, okay, and then take it after, to take the back reaction into account actually. Otherwise the back reaction won't be taken into account. Yeah. So you can actually do this similarly in the bulk, and where okay, maybe I can talk to you about it, where actually the fact that there is this ingoing particle shifts the horizon. It's a similar calculation as this Schenker and Stanford and so on. But this is a way of doing this in the CFT. We can reproduce those similar answers. So this is the jump. Okay. And what we do is basically we repeat this. If we repeat it with this ingoing particle having a charge also, having a spin 3 charge. So let's repeat this whole thing with the primary having a spin 3 charge. And that can be done because basically how we are, in terms of the geometry, how one is modeling the primary is a conical defect. And there are spin 3 conical defects. And we can, there is a connection for them in this SL3 Chern-Simons. And so we can, there is a holographic way of treating it also, but there is an equivalent conformal theory way of treating it using W3 blocks. Okay. And this is what we observe. So here's the jump. Okay, so if you want the parameters, I have it, but this is the jump. And so this is the jump without the spin 3 charge turned on, Q. Okay, so let's keep the spin 3 charge is Q. Okay, I didn't call it, I didn't tell you again, but this is the spin 3 charge set to 0. And then here the spin 3 charge, and everything has a finite width and so on, and this is a particular length L1 and L2. And I hike up the spin 3 charge, there is this crest sort of developing, and then really this, the entanglement entropy, the jump behaves very badly after that, after some interval. Now, again, to get a particular compact, of course, this is by seeing the pictures of the answer, but to get a compact expression, we can again do the scaling limit. So here's the scaling limit. We demand the total spin 3 charge of that excitation is finite. So this is a particular scaling of the, so again, this is just dimension. And so we scale the spin 3 charge to this and keep Q finite. And when we do that, here is the expression for the jump. So you see, this is the expression when there is only the conformal dimension without the spin 3. And here, there's this extra term. And it's negative. Okay. So the log, in fact, is becoming, log of the argument is becoming negative at a particular value, actually. And, it's ill-behaved after that. And to avoid this, this is the bound we found, actually. So we had to do this. And if you rewrite it in terms of the charge, W, and the conformal dimension, after removing the epsilons and so on, this is the particular bound we have taken. So the charge is bounded, the spin 3 charge is bounded by the conformal dimension in this particular manner. And of course, the bound in the charge, which we saw, can also be seen from looking at the chaos bound. Okay. So what we saw by examining the behavior of the entanglement entropy, there seems to be a bad behavior. And if you just demand that the entanglement entropy behaves well, we get this bound. If there is a very close relation between these correlators which we are evaluating and the OTO correlators, okay, which we observe. Okay, so this is, though this thing of this pulse propagating inside is called the quench correlator, but there is a very simple analytic continuation of that, where from which you can get the OTO correlator. Okay. And that we found that, and from there, recall again, there are two parameters, L1 and L2. Okay. These are the parameters for our problem, the epsilon, the width of the pulse, and the time. Okay. These are the parameters. And in the OTO correlator, there is this epsilon, which basically is a regulator between the two operators, and that is shrunk to 0, and therefore you have to look at, when cross ratios become 1 or 0, and there is a time there too, okay, the time separating the two operators. And in fact, there is a very simple analytic continuation to relate it, okay. So essentially going into this entangling interval is essentially going to the second sheet, as some people who are into OTO will know that you are going into the second sheet, and then you have to stay there, okay, to observe the large time behavior. And that's what, so from the quench correlator, you can easily go into the OTO correlator, and we do that. Okay, this is a little technical to show that the quench correlator is the same as the OTO, but from there we can go and we can evaluate the OTO correlators also here. And this is the expression. And you see that this bound essentially ensures that this development is more dominant, okay, than the spin 3 development. So this is the spin 3 Lyapunov exponent, and this is the usual Lyapunov exponent, and this bound ensures that. Okay. The bound which we just found from entanglement entropy consideration ensures this. And so this is the conclusion that this bound also ensures that the chaos bound is satisfied. And in fact, you can get this bound because we wanted to cross-check this in several ways. So this bound can also be ensured by looking at scrambling time. Now you see, if you evaluate the scrambling time in the BTZ with this excitation going in, you get this particular expression for the scrambling time. And you see, if the Q is 0, it's the usual Lyapunov exponent and the usual dependence. And then there's the divergence when the saturation of bound is there. And then if this is negligible, it's the next exponent, spin 3 exponent, which is controlling it. And again, that feature is seen here. So there's this bound which we can see by various physical reasons, the chaos bound as well as this just entanglement entropy. And in fact, we put this paper out, and the very next day, unfortunately, very next day, these authors came in, and they, I don't know for what reason, they were looking at states in W3 theory, and they looked at this particular Kac-Determinant, okay? So basically the spin, this states have both conformal dimension and spin 3 charge, and this particular Kac-Determinant, you can evaluate using just the W3 algebra, okay? And the constraint that, the eigenvalues of this Kac-Determinant is positive, okay? Is like if you demand that level 1 is positive and the rest for all the constraints are satisfied, they showed that, and they obtained this particular constraint. So this is the particular constraint they arrived at large C. So I've taken their constraint and pushed it to the large C limit, and this is a particular constraint. It's certainly different from our constraint. So we compared our constraint with that. So our constraint was this, or this, just a simple thing. And if you compare our constraints, so this is the region of Hartmann et al.'s constraint, and our constraint is here. So we are, we are not as constraining as theirs. Actually, theirs is the more right one. So I guess because of the scaling limits and everything, we are not as good as theirs. But these physical reasons automatically give this very nice bounds on charges. So ours is consistent certainly with their constraint, but we are not, we didn't reach theirs actually because of the approximations we sort of do. So this just wanted to point out that there's very physically different reasons, the entanglement entropy, OTOs, and so on, lead to the same unitarity constraints. So can we make this sort of slightly sort of more a little bit, see it much more directly a little bit. So this is a work in progress, actually. So I've shown two things, and can we see this a little bit more sort of directly? And so what we want to show is basically a presence of the state which is, does not satisfy the unitary bound, violates the chaos bound also. Can we see this more directly? And so here we consider this particular density matrix. Okay. So this is the thermal state, but we insert an operator, okay, of high dimension, okay, on it at 0 and infinity. And we actually evaluate, say for instance, just do the stress tensor on this. Okay, if you just evaluate the stress tensor, it's a simple 3-point function. And since it's a finite temperature, you have to do it on a cylinder. You get this answer. This is, everybody in CFT would have done this at some point. And you get this answer. And you see that the answer differs from the thermal, the usual thermal C pi squared by 6 beta squared by this shift, by this 1 minus 24 by C shift. And so roughly speaking, the effective temperature shifts by this nice expression. Okay. And what is the OTO, okay, of 4 operators in this particular state, rho O. I mean, basically the state is a thermal state, but just to remember, the state is a thermal state. Oh, I shouldn't cross. It's a thermal state. Okay. But excited by a heavy operator, a definite heavy operator. And so as a preliminary step, let's probe first, first I did the 1-point function. You see that effective temperature is changed. And let's probe it by a 4-point function, okay, of basically, to probe it by 2 light operators. Okay. And here it is. But it basically reduces to a 4-point function because of the presence of these heavy guys at beta. And if you evaluate this using the large C conformal block, using this large C conformal block, you can evaluate that correlator because these are light. You can evaluate it, and you get this answer that effectively the temperature is beta prime, the new temperature. So the presence of this operator basically shifts the temperature when you probe it by light operators to this beta prime. And you can use this result for evaluating entanglement entropy, and you see this dependence changes because of this particular presence of this operator. And for OTO, actually you need the 6-point function in this particular state. You need the 6-point function. And you can do the 6-point function also using the large C answers. You can do the 6-point function, and effectively it turns out, I mean, you can go through the steps, and you can show that it's a 4-point function at the effective temperature difference, just like I showed you the 2-point function at this effective temperature beta prime. And if you evaluate the OTOs in this particular state, usually you evaluate in the thermal state, but now you're evaluating it in this particular excited state. And you see it changes this beta prime dependence. So the Lyapunov exponent changes by this particular manner, in this particular manner. And of course, if the state satisfies the unitary bound, then of course the Lyapunov exponent is okay. But if the state is less than that, it violates the bound. It violates the bound, which is us. So we wanted to see it directly. So this is one way of seeing it directly. And is there a system such that this particular state is realized? Okay. And in fact, there is one. Okay. So if you consider Chern-Simons theory with this particular group, okay, this is a weird group. It was studied earlier by Polyakov and Barshatsky, and it's essentially a Virasoro algebra. It's almost like an n equals 2 algebra, but it's bosonic. Okay, and if you study this, okay, this particular algebra, and there is a Chern-Simons theory associated with this particular algebra. And the algebra actually arises by a different embedding, a different SL2 embedding in SL3. So this is the usual SL3, and this is the new W32 algebra. So the SL2s are related to the SL3s in this manner. Okay. This is the way this algebra is realized, and you can actually have a Chern-Simons theory associated with this algebra. And if you consider the BTZ So you think that it's a BTZ-like solution. So you impose the same periodicity condition for the temperature as a BTZ. Okay. And what you see, okay, this connection is the same form as the BTZ. And the difference in the connection is basically you're using the different matrices, L hat versus the L. And the level of the Chern-Simons is related by this. And if you impose the same holonomy condition as the BTZ, this is usually what is done. So you impose the same holonomy condition as the BTZ, and you see the stress tensor. You can read out the stress tensor. It shifts. Okay. And from the shift, okay, just like the way I showed you, because of the presence of the operator, the stress tensor is no longer that of the BTZ, actually. It's slightly different. If you find it, you'll find that there is an operator of dimension minus C by 8 here, okay, in this particular thing. This particular theory, and you can go ahead and calculate the entanglement entropy. And in fact, these authors had considered this theory earlier, and it certainly agrees with that, and with the agreed interpretation of the fact that there are these heavy operators in the vacuum. And if you evaluate the Lyapunov exponent, certainly it violates it. So we have done some more tests with it, and it satisfies some consistent picture of this particular thing. So maybe I'll stop here. I stopped earlier. That we discussed two constraints, okay, in this theory. One of them was three-dimensional constraint of the allowed parameter spaces of all conformal field theories in 3 dimensions. And one is a little bit more specific, where we constrained charges of certain higher spin charges in this particular thing. And as you saw that the physical considerations which we used to obtain these constraints were very different. They were like entanglement entropy, the average null energy condition, but somehow all of them are related to unitarity. And we saw that actually in some more directly in the 2-dimensional example. Okay. And so that's sort of where I end my talk here.
So this beta prime business, where you basically get an effective temperature for the purposes of calculating OTOs and entanglement entropies and expectation values. So this sounds like a generalization of ETH, where instead of having a pure excited state, which is effectively equivalent to a thermal state for local observables, you have a state of the form you said, which is excited from a thermal state and gives effectively another thermal state at a higher temperature. Is that?
Maybe I haven't actually seen the connection. I didn't like look at it in that direction.
I mean, if you took, in your story, you took beta to infinity, you would recover ETH, it sounds like.
Okay. Let me see the formula. Roughly speaking, this is the formula. This is sort of, the original.
I think, I mean.
Yeah. Here's the shift. So beta prime is beta divided by this. That's the shift.
Right, so you probably have to scale things in some way, but it seems morally like some generalization of ETH.
But yeah, we see this, of course, I mean, we saw it as a calculational tool. I mean, when we calculated higher point functions, it reduced to a lower point function at a different temperature. I mean, basically shifted the vacuum's temperature, actually. That's what it did. I mean, for instance, here, this is the easiest to see. So we inserted these things, and then we use the conformal block, which is known, but use it at temperature beta. But then the answer we get is for the beta prime. Yeah, so that, see that.
Temperature is cooler. Huh? Is that right? Effective temperature is cooler after you increase delta, which is
after you yeah, I think so.
So
sort of counterintuitive. Yeah, I don't know why it happens actually. But this is coming from
no. Beta prime is
higher when delta is positive. But this comes from here. I mean, there's nothing. I mean, it's a very simple calculation. So this is the usual stress tensor part. Yeah, we were puzzled about this. This is the stress tensor part. This is the usual dimension of the operator, and this is the usual thermal vacuum, C minus pi squared by delta. And this is the shift. So you take this minus C pi squared by beta squared out, is 1 minus 24 delta by C.
Did you get minus C pi square by 6 beta square? Shouldn't it be plus?
Well, it's an Euclidean. It's an Euclidean. It's minus. I mean, if you evaluate the Shorttian,
it should be just the positive pressure, right?
Yeah, but if you evaluate the Shorttian, it comes out to be minus. Yeah, you can try that. I mean, yeah, it comes out minus C by pi squared. It's like the ground state energy. Yeah, but it's in Euclidean. You have to, if you transform in Minkowski, you get the plus. You get the plus energy. This is purely from the short. Yes.
I would like to ask you about this three-dimensional picture with this circle. So I guess that the circle corresponds to, holographically, precisely to the full set of hairspin gauge theories in the bulk.
Yeah.
And my question is whether, in this case, this circle is characterized by some decoupling of null states, which means the degeneracy of Kac-Determinant in some sense in the other language.
Yeah.
So.
Yeah, that's what we have been trying to work towards that, actually. Trying to understand the fact that the saturation of bounds is related to some presence of the null states and so on. I mean, presence of the saturation of the unitarity bounds, basically.
Yeah.
But so right now, what we have been using is basically reflection positivity in CFT to arrive at this particular saturation.
Yeah.
That's what we've been using.
Okay, thanks.
Okay, so let's thank Justin again. We break for lunch. Yeah.